In 1783, scientist John Mitchell was thinking differently. If we fire a cannonball vertically upward from Earth, it will slow down at some point, it will stop moving, and fall back to the surface. If we want the cannonball to escape from Earth, it needs to travel at some value. That's 11.2 kilometers per second. We get this number from legendary scientist Isaac Newton's gravity equations. At this speed, Earth's gravity would not be strong enough to stop the object, so it would continue on its journey and would escape from Earth. Similarly, every object in the universe has an escape velocity, which varies because an object's strength of gravitational pull depends on its mass. For example, Jupiter's mass is 318 times greater than Earth. So if we were to escape from Jupiter's gravitational pull, we would need to drive our rocket at 59.7 kilometers per second. For the Sun, this would be 615 kilometers per second. These speeds are very low compared to the speed of light, which is 300,000 kilometers per second. Mitchell thought if a star had a mass many times greater than our Sun, that star's escape velocity would be greater than the speed of light. So from that star, light couldn't escape because light will be dragged by the star's intense gravity. Since we can't see the light from that star, it will appear dark. So he called that hypothetical star the dark star. To understand these dark stars, we need to start with how black holes are formed. Every star is formed from hydrogen gas clouds, so the star is filled with hydrogen atoms, and due to the extreme pressure of the inner core, hydrogen atoms combine, forming helium atoms. In this process, some of the mass is converted into pure energy, then is released in the form of light and heat. This is called nuclear fusion. For example, our Sun releases energy equal to 10 billion hydrogen bombs each second. A star's gravity always pulls the star inward, and energy released from nuclear fusion pushes the star outward. This process happens continuously, so these forces balance each other out and keep the star stable. But after some billion years, all the hydrogen atoms in the star will run out, and then only the helium atoms will be left. Again, helium atoms are involved in nuclear fusion to produce carbon atoms. This nuclear fusion cycle continues for some billion years until it turns into iron atoms. Iron atoms are extremely stable, so the stars are not massive enough to trigger its fusion process. So now, energy released from the star's core completely stops, so there is no outward push to keep the star stable. The inward pull force of gravity wins, crushing the star inwards, and in a fraction of a second, the entire star shrinks into a tiny volume, then violently explodes. This is called a supernova. Depending upon the star's mass, it will either become a white dwarf or a neutron star. For example, once our Sun dies, it will become a white dwarf. But when a star more than 20 times more massive than our Sun collapses, it becomes a black hole. So black holes are regions where an enormous amount of mass is packed into a tiny volume. That density becomes unthinkable. For example, if we wanted to turn our 1.4 million kilometer diameter Sun into a black hole, we would have to shrink it to a diameter of 3 kilometers. Similarly, if we wanted to turn Earth into a black hole, we would need to translate its entire mass into a sphere, just 2 centimeters wide. As a result, the object collapses and becomes a black hole. So the center of the black hole's density becomes infinite. Now let's take a look at the nature of Einstein's gravity. He described it in his general theory of relativity in 1915, which introduced the concept of space-time. Even though Isaac Newton devised the extraordinary equations for gravity, he was not able to explain what really causes it. For example, everything matches well with his mathematical equations. The Earth orbits the Sun, the Moon orbits Earth, and everything works perfectly. At the same time, the distance between Earth to Sun is 150 million kilometers. But how and what invisible force acts on such a distance? He couldn't explain this. Einstein explained gravity with space-time curvature. According to him, gravity is not a force. Every object in this universe has a mass, which bends space-time depending on how much or how little is present. The more mass, the more the curvature in space-time. Objects follow this curved path. The Sun bends space-time, so Earth moves through that curved path. This is how gravity works. When Einstein introduced the concept of space-time curvature, it was not widely recognized, but later on, it was proved in many ways, such as via gravitational lensing and the orbital path of Mercury. Gravitational lensing means light also follows the space-time curvature, so we can see a star from Earth which is directly hidden by our Sun. Similarly, black holes have an incredible mass and density, therefore they bend space-time to a huge degree. As we already know, light also follows the space-time curvature. Black holes curve space-time to an extreme or maybe even infinite, so even light can escape from a black hole's curvature. Since light is massless and is the fastest thing in our universe, that means nothing can escape from the black hole. But light can escape further distance from the black hole. That place is called the event horizon, the boundary between the universe and the black hole. The event horizon is not a physical part of a black hole. From the event horizon region, gravity becomes so strong that greater than escape velocity of speed of light. So the escape velocity at the event horizon would be faster than the speed of light, which makes it impossible for light to escape. After that event horizon, escape velocity or space-time curvature increases tremendously. So if you travel to a black hole, space-time curvature or gravity becomes stronger and stronger. Once you cross the event horizon, there is no way to return. You are trapped completely. Black holes eat nearby stars, planets, and further increase its event horizon, but we don't know exactly where all that matter, energy, and information are going. As we already saw, black holes have zero volume, so are they all really going into this zero volume? Zero volume means singularity. The laws of our universe cannot explain what the singularity is because singularities cannot really be possible in our universe. Some have hypothesized that this zero volume thing with infinite density exists in the higher dimensions. Our universe also started from a singularity. Does that mean our universe began with black holes singularity that existed in another universe? We don't know. Einstein's general relativity equations predicted that black holes might exist in our universe. However, later on he reneged on his own predictions. He thought that an object cannot be contracted after a certain level. Space-time breaks down at the singularity. In fact, it marks the end of space and time themselves. So he claimed gravitational collapse is not possible. But in 1963, the first quasar was discovered. And this provided the first real evidence for the existence of black holes. Quasars are the high-energy beams emitted from black holes. When nearby objects are caught in the black hole's gravitational well, some of the object's mass is converted into pure energy and released as a high radiation beam due to the extreme gravity and friction. This phenomenon occurs in the center of the galaxy and likely means that every galactic center has a supermassive black hole. In later years, quasars were discovered in many different galaxies. General relativity also predicted the existence of gravitational waves. So what is a gravitational wave? For example, consider space-time as a pond. When you drop a rock into that pond, it creates ripples on the surface. Similarly, when an object is in motion, it creates gravitational waves, but those ripples are very tiny. But when a high-density, massive thing like a neutron star or black hole moves at high speed, it creates larger waves in space-time. So how can those objects move? That's when binary systems come into play. It's possible for two galaxies to collide. Each galaxy has black holes. So the two black holes can become caught in each other's gravitational wells and collide. Before the collision, they orbit each other and create big enough ripples in space-time for us to detect. Those waves travel at the speed of light, and by the time they reach Earth, they will have lost much of their original frequency, but are still detectable. The first evidence for gravitational waves came in 1974, when physicists Russell Hulse and Joseph Taylor discovered a pair of neutron stars 21,000 light-years from Earth that seemed to behave in a curious pattern. They deduced that the stars were orbiting each other in such a way that they must be losing energy in the form of gravitational waves. Then in 2015, for the first time, scientists observed direct evidence of gravitational waves from black holes. They used a very sensitive instrument called the Laser Interferometer Gravitational Wave Observatory. The black hole collision they detected occurred 1.3 billion years ago, but the waves only reached Earth in 2015. Because we already know the speed of gravitational waves is finite and travels at the speed of light. We know it took that much time to reach Earth. Those pieces of evidence confirm the existence of black holes, but one of the greatest achievements of mankind happened in 2019. Yes, we took a photograph of a black hole. Scientists zoomed in on the center of a distant galaxy named M87 for years. It is located 55 million light-years away from Earth. Capturing a black hole is not easy. We need a telescope the size of our Earth. So scientists use a worldwide network of radio telescopes called the Event Horizon Telescope. These 8 telescopes are located in different countries all over the world and are linked to each other. All those telescopes were pointed in the center of the M87 galaxy and collected data for years. The data they carefully collected and merged, and the result we got was the first ever picture of a black hole with its orbiting disk of light. As we have already seen, there is a supermassive black hole in each and every galactic center. Likewise, there is a black hole at the center of our Milky Way galaxy called Sagittarius A. So our solar system and everything in our galaxy is orbiting this black hole, but observing this black hole is really difficult. So scientists used other ways to detect Sagittarius A. They observed the orbital path of the stars located near Sagittarius A. Those stars appeared to orbit strangely, meaning that when they came near the black hole, their orbiting speed increased tremendously. So they thought there must be an extreme gravitational object. That's why stars are orbiting strangely. Over years of observation, scientists confirmed there is a supermassive black hole, and later in 2022, the photo of Sagittarius A was taken successfully. So one of the predictions from Einstein's general relativity theory has been proved, but we still don't know exactly how black holes behave. While we know some of the properties of the event horizon, we still have a long way to go to explore the inside of the event horizon. Since we don't have a clue about what exactly a singularity is, it's really puzzling how space and time act inside black holes. One confirmed thing is that black holes exist in our universe, and black holes curve space-time to an extreme degree. So the time slows down near the black holes. We will see how time slows down near the black hole in another video soon.